Okay, so yes, I've been working with Slava, and we're talking about the idea of an interstellar precursor mission to the solar gravity lens focus. And I'll go slower than Slava, but so that you can assimilate all he said in that rapid talk. That was very good, Slava. Thank you. Um, so, and this is one of the slides that we referred to. We did a study at the Keck Institute for Space Studies at Caltech. We had a workshop, and we then delved in some depth into ideas for exploring using science and technology to explore the interstellar medium, to go beyond where Voyager has gone and into the interstellar medium. As Slav had already pointed out, the area from the edge of our solar system, or at least the edge of the fields and particles influencing our solar system, the heliopause to Alpha Centauri, is pretty empty. And what attracted me right away was that the fact that the solar gravity lens not only offered this tremendous scientific potential that we just heard about, but there was a sort of an intermediate goal. It was something that was very challenging to read. At least I thought a few weeks ago it was challenging. Now I realize it's just a tiny fraction of what Starshot is going to do, so it's not challenging anymore. But that it was a very challenging goal to get out to 550, 600, 700 AU, and at the same time to do the kind of measurements we would want to do there. So I thought it was the right interim step toward thinking interstellar. So in the Keck Institute study, as I said, science and enabling technologies to explore the interstellar medium. Basically, the main result of it was a focus on what would be the next step, sort of in conjunction with the desire of the heliophysics community to move beyond Voyager, to make measurements deeper into the interstellar medium at a much faster mission than Voyager was doing. And so the main result of it was a nominal mission design, which used basically, I don't know if you call it conventional propulsion, a solid rocket motor to give a very large delta V in an Oberth maneuver very near the sun, just a few solar radii perihelion, and give a fast exit velocity from the solar system in order to get into the interstellar medium quickly. And the velocities that could be achieved in this technique were in the order of 10 to 12 AU per year. But that's as good as you can do by that technique. And to do beyond that, you really need other techniques, and that's where solar sailing and then laser sailing and other techniques will come into play. In our study, we identified further goals, deeper goals, beyond just going to the next step beyond Voyager, beyond that immediate objective, but really to get into the pure interstellar medium, which begins, no one knows where, but on the approximate order of magnitude of perhaps 300 AU, to get out to the 550 plus AU, maybe to 1,000 AU, to do the solar gravity lens focus measurements, and to make that as the and to see what kind of technology steps would be needed there. We looked at radio communication, optical communication. We identified ideas for using the sail itself as either a reflector for optical communications or as an antenna for solar communications. One interesting thing is you still have to power the spacecraft even if it's a sail, and there we had a new technique of new results in radioisotope electric power, which could power relatively small Hall thrusters and add a few AU per year to our basic capability, as much as 6 AU per year to the velocity we could achieve with the solar sail trajectory, and also provide the power to the spacecraft. In the study, we identified several sail options that we want to go into for more depth to look at. One that I'll talk about a lot is the use of solar sails with a nano spacecraft, getting as much area as we can practically and as low a mass as possible to get, and this is one design you'll see over there on the left with a spinning solar sail with a 2.5 micron film. Now that's kind of state-of-the-art technology, if you will. It's not been done, but it's on the order of what we think we can achieve, and the number you see there for its capability of 62 meters squared per kilogram, and I'll come back to that unit. my contribution to the study was to get the units right. I did all the velocities in AU per year, because that's the way I can think, and then and all the spacecraft parameters in meters squared per kilogram, because that immediately tells you what your design requirements are for the size of the sail and the mass of the spacecraft. And so 62 meters squared per kilogram is very, very good. It's much better than we have now. The light sail that the Planetary Society is building is about 6 meters squared per kilogram. I think the NEA Scout mission that NASA is going to do is about 8 meters squared per kilogram, I think. So it's still a big order of improvement, but as you'll see in the next couple of charts, it's not enough. We have to get better than that. The other kind of sails that got some publicity last week that people were interested in studying is electric sails. Electric sails actually do use the solar wind. For years I've been lecturing about solar sails, saying it's not the wind, it's photon pressure. But electric sails do use the solar wind, the electrons and protons that are streaming out of the sun. And so that force is 1,000 times less. So you might think, well, why would you want to use it? Because as it turns out that the calculation of the way it works by putting electric power into long tether wires and forming a plasma sheath around them, you can actually ride on that kind of on wind with not a 1 over r squared loss of power as you go out from the sun, but 1 over r to the 7/6 power, so that you actually the force stays with you a lot longer, and so it has advantages, at least for a while. As you get out to deeper and deeper distances, I think the advantage of light sails is still better. And we got into laser sailing, and Phil Loeb was part of our study team, and we spent a lot of time looking at the possibilities for laser sails. And I must say, at the time, I had been accustomed to thinking of laser sails as beaming the power from Earth, following it, trying to focus it over interstellar distances, and so that was a little daunting, and I'm very pleased with the new concept that Starshot has come up with basically putting in that, just like we do in solar sails, we want to put all that energy in the solar system and then fly out fast. The same thing with the laser sail, that it's putting all the energy in that first 2 minutes of the powered sail flight, and then coasting out to the interstellar distances. So we looked at that, and we came up with some ideas for near-term technology demonstrations that might advance this topic while we're theoretically studying it. And one we're actually planning to do next year. We're going to do a ground-based laser illumination of light sail, which is built by the Planetary Society, project that I got started a few years ago with a nano spacecraft, a 3U CubeSat 5 kilogram spacecraft, 4 by 4 meter, roughly 4 by 4 meter sail, flying at 800 kilometer altitude, so that you're above the atmosphere. You can get no drag effects, and after that basic sail is put in orbit and verifies that it's flying under solar sail power, if you will, we have a plan to actually illuminate it with a ground-based laser from Albuquerque and measure that the micro push that you get on this, and really would be the first laser propulsion experiment, and I think it's very relevant to what we're doing here. So we kind of identified this as a first step laser sail demonstration. Now, Phil will tell us over and over again that laser sails are not solar sails, but certainly they have the same technological elements, the highly reflective material and the structural approach to them. So this, I think, will be very, very relevant. And so that's kind of one in-space step we can take to interstellar flight, is to do this and do it, as I say, next year, because that's when the flight is scheduled. I'd like to, Starshot has gotten me thinking, and now I'm deviating from what we did in the KISS study into my own thinking. I'd like to, Starshot has got me thinking about, we have to take steps further into, we've never built a 1 kilogram spacecraft, let alone a 1 gram spacecraft to fly. And so I'd like to get a sub-kilogram spacecraft with a modest-sized sail. And it turns out if we could do that, we could fly actually at the same thrust level, the same force level that the asteroid redirect mission is with its solar power, solar electric spacecraft, and that would make a nice companion spacecraft to observe it. And so we could get a free launch on that mission and maybe fly a picosail, sub-kilogram spacecraft, with all the electronics we can think of doing as an experiment. This would be totally experimental. It is not part of the main mission at all, but it could fly as soon as the early 2020s. And then I'm going to talk the rest of the talk here about trying to take the next step in really doing a solar gravity lens mission, maybe in the mid-2020s as a step toward that interstellar precursor that I mentioned. Well, I won't spend any time on this because basically Slav has explained it all here, but he explained that it's a focal line that moves out beyond 550 AU. That's actually good because if we had to rendezvous at a focal point, that would be another huge propulsion requirement that we have no idea how we could do. So this way, all we have to do is aim to go right down the focal line with a little bit of maneuvering capability to do that multi-pixel sampling that he described in the Einstein ring. It truly would be an interstellar precursor idea because scientifically, the goal would be, as he described, to identify a habitable planet. You have a habitable planet. Now, obviously, you have to have your target in mind before you can aim for the right focal line. So this is presuming that you have chosen your target or multiple targets if you have multiple spacecraft. And if you're doing this with small spacecraft, that may turn out to be practical. But then this might be a target for the eventual interstellar flight that you could image early on, and it would be a technological step both in terms of its milestone and its technology of getting there, and testing out all of these spacecraft components that we're going to want to use. And Slav has also mentioned the coronagraph. So what's new? How did this subject come up? And this is kind of what got me into the whole thing. I've been working on solar sails for a long time, and we had even attempted a flight with one with a 110 kilogram spacecraft on a Russian launch vehicle back in 2005, and we were determined to try again. That one was lost due to a launch vehicle failure. Soviet ICBMs were not as good as they were advertised, at least advertised by them. So we lost that one. But and it turned out NASA had started out on this nanosail concept, and they had lost their spacecraft also due to a launch vehicle failure, an American rocket, actually one of the first Falcon flight. But so we began discussing, well, we could fly that kind of a nanosail. And first, NASA thought they'd actually give us their spare nanosail. Turned out they didn't have, it didn't work out that way, and we could actually improve on it by adding radio and instrumentation to it and cameras. And so we built our own, and you see it there in the left-hand corner. It's a light sail that's planned to fly. You see right above it, that's the full-scale sail laid out to and the nice thing about small sails is you can do it in a garage or in a modest-sized room. And then the other thing that's going on is these evolving technologies. Technology is, as we've heard over and over again at this conference, Moore's law is just driving all the technologies down. And you look at, and this is something I wrote into my book last year, is trying to make the argument that the future is going to be small spacecraft. In the future of interstellar flight, we have to take into account the growth of these technologies. We're going to have not just small, but we're going to have more capacity, more information, and all the action is going to be on information processing from these future spacecraft. And this now chart is superseded by the one that Yuri Milner showed last night and Pete showed this morning. This is Starshot's projection of evolving technologies. It's the same order of magnitude of kinds of improvements that will come into play here. Now, I think, as I said earlier, before we get to the 1 gram spacecraft, we should get to the 1 kilogram spacecraft, to the 500 gram spacecraft, and start building and flying and getting some experience with some of these. I won't spend much time on why solar sails. we all know sunlight reflects off the sail. I'll just answer the basic question in case you're uninitiated, which is the same question I get in every conference is, how can you tack with them? But basically, you control the direction of the sail, an attitude control in one way or another, and you can either add velocity to go outward or subtract velocity to go inward. I already commented on it. This is a precursor to laser sails, at least in a technology sense. There's really only three design parameters: mass, area, and the perihelion distance. You want large area to get as many photons as you can. You want as light a mass so that all your momentum transfer goes into velocity and not into as much as possible. And you want a low perihelion, both to pick up the solar power that's increased down there, and also to apply your delta V at the lowest point on the ellipse so that you can have the maximum effect on the aphelion and essentially make it infinite, so you have an escape trajectory that goes out of the solar system. So you get down to low perihelion either by multiple passes of solar sail trajectory or just launch to a low perihelion. And this is a chart we did to sort of parametrically study the possibilities of design parameters. Area to mass ratio is the x-axis, speed in AU per year is the y-axis, and three different perihelion distances there. Now remember, I told you that today's solar sails are all down in the 5 to 10 category, so they're not even on this graph. Even the 62 meters squared per kilogram spacecraft that I talked about earlier is not on this. And where I think we'd like to be for the solar gravity lens mission is something like a 30 by 30 meter sail with a 1 kilogram spacecraft. That would put us out at 900 there, and if we can make that with a material that can withstand down to 0.1 AU, which theoretically we can, then we could go at a rate of 25 AU per year, even getting to 20 AU with some of these other design parameters on this. Would be quite an achievement and quite an increase in capability from where we are today. So mission goals for a solar gravity lens focus mission: the high resolution imaging that we just talked about at the kilometer scale type resolution on an exoplanet, as Slava mentioned, the only way to do it. Exploration, to go further and deeper into the interstellar medium to really begin our outward journey from the solar system. And technology, study what we need to study in order to get very thin, very large sails operating reliably in space and getting very low mass spacecraft, getting to the sub-kilogram level. So I think in all three senses, this becomes an interstellar precursor for Starshot or for any other ideas of exploration beyond the solar system. I picked three example kinds of things. One I call conventional. There's really nothing conventional about a 200 by 200 meter sail with a 100 kilogram spacecraft, but that's, if you gave this job to a NASA center or a company today, that's probably what they would design, and it would take about 32 years to reach 550 AU. I want to test and suggest that we want to test the lower mass spacecraft, with a 1 kilogram size spacecraft. We do it with a more modest sail. We can get higher area to mass ratios, and we can actually get out there faster. I showed an earlier example of maybe even a 200 by 200. That's what I would do today, is try to do a larger sail than this 12.5 meter thing. But I chose the 12.5 meters because that's the size of the Starshot sail. If we had the Starshot spacecraft and you want to just put it through some exercise, you could just do it. It would get out to the solar gravity lens focus in 5 years. That'd be pretty good. So further, as same point that Slava was making, these are ideas at this point. We're brainstorming. Further idea, we have to find out how to create that image and go through the whole simulation of that. We have to study the spacecraft requirements to fly within the Einstein ring and do the maneuvering necessary. And we have to specify what kind of mission design and system requirements we want to do. And so that's what we're proposing to study as a follow-on to our initial ideas here. That's it. Thank you.